So let's look at this example. A survey was conducted of hourly wages for a sample of workers in 2 industries at 3 locations in Ohio. Part of the purpose of the survey was to determine if differences exist in both industry type and location. The sample data are shown on the next slide. So the sample data on the next slide, I've actually read into Excel, and I'm going to go over to Excel. But in this question, we've got 2 factors at play. One factor is industry type, and there are 2 industries, so there's 2 different levels. And the second factor is location, and there are 3 different locations. So both of these may impact on the hourly wages, the industry you work in, and also the location that you work in. If we can look at the next page briefly, this is the actual data that they were given. So they've been to Industry 1 and Industry 2, and they've got the 3 different locations of Cincinnati, Cleveland, and Columbus. And we're going to run a 2-factor test. Now you can see this is a 2-factor test with replication, because when they went to Cincinnati and went to Industry 1 and they asked people there, how much do you earn? They asked this person, then they asked the second person. So they repeated the experiment. That's why it's with replication or repetition. And they actually did it a 3rd time here. They didn't have to do it a 3rd time. If they do it a 2nd time, that's enough to be a 2-factor with replication. But they actually repeated the experiment 3 times, and they also did the same thing for Industry 2. They went to 3 different places to find out what the hourly wages are. So this is going to be a 2-factor with replication question. What I've done here is I've read in the data, and I've actually read in the table that you should be getting. And again, you need to be able to navigate around this table. A is going to represent the number of treatments of factor A, number of levels of factor A. Likewise for factor B, that's what B is. And R is the number of times you repeated the experiment or replicated the experiment. And in our case, what I just showed you, it was 3 times. So we can go into Excel and up here, and then we can ask Excel to do the work for us. So we've got data analysis. So this is going to be 2-factor with replication. And we're going to read in all our data. It's interesting, it doesn't ask you about labels, so it's actually expecting you to put everything in. Now, rows per column, I've put in as 3. And why is it 3? Well, because we repeated the experiment 3 times. That's just asking you how many times did you repeat the experiment. And further down in the table, where it had R, that's the number of times we repeated the experiment. Let alpha be 5%. Let's put our output in column H and get the results. Oops, you have to be careful here because sometimes it goes a bit haywire. Doesn't like it sometimes. Okay. And there are the results. And maybe I can make this a tiny bit smaller so we can see it. There you go. So it gives us all the breakdown of the results for Industry 1, Industry 2, and so on and so forth. But this is where the bulk of the results are. And so make that so it makes it easy for us to see. A little bit bigger. Again, when we look at the factor A, factor B over here in the table, and we look over here, we have to figure out what all this means. What does sample columns interactual within means? What does it all mean? Well, let's start off with columns. Columns may be the easiest one to start. What do we have in our columns? In our columns, we have the different locations. See? Different locations in the columns. So I can actually put columns / locations. Now, when it's referring to sample is like asking the number of times we repeated the experiment and what did we repeat the experiment for, and it's basically talking about the industry. Okay, so we repeated it 3 times for the industry. It's like we took a sample of 3 for Industry 1 and a sample of 3 for Industry 2. Okay, so when we're talking about sample, we're actually talking about the factor industry. So I'm going to put /industry. And interaction, well, interaction, at least interaction is the same, and within it's just going to be the error terms. And we can just start getting our results from here. And now, incidentally, to work out f critical, you still use exactly the same method we did before. It's going to be f dot inverse dot right. You can put alpha as 0.005, and the two sets of degrees of freedom are whatever you use to get your f test statistic. So, for example, to get this f test statistic, I'm going to divide out this figure by the error figure. You remember, you always divide out by the error. So the degrees of freedom I would use to find in anything in this first row is this guy and this guy. And you should try it out to make sure that you've picked up how to do it. But let's get the results out for here. And there's 3 different results we can get. So let's draw out the results. The first result that we can look at, here is going to be testing. Well, it's up to us what we do first. Let's test industry. So how many industries did we have? We had 2 industries, yeah? So we're going to test to see if the average for industry 1 is equal to the average for industry 2. We're talking about hourly wages. And so this is the industry part, and the is going to be not the same. The alternative is that not equal. They're not all equal. But there's only 2 of them, so let's just put not equal. And to test this, we can use the critical value approach or the p-value approach. So if we want to use the critical value approach, I'm just going to do our graph. So it's always the same thing that we're going to be doing. Critical value is going to be here. Do not reject is always going to be to the left for these questions. So this is going to be the do not reject over here. And the reject is going to be over in red over here. And let's see, so if we're talking about the industry, which is the first one in here, the critical value is going to be 4.7. And the test statistics, that's critical value, the test statistics would be 4.18. Oh, so 4.18 is going to be about here, so the conclusion is do not reject, so we go with it. So the hourly wages between the industries appears to be the same. And you could also use the p-value to get a do not reject. The way you do that, remember the p-value approach, if alpha is greater than or equal to the p-value, that implies you reject H0. And if alpha is less than the p-value, you do not reject H0. So I used a p-value of 5% for this question. And you can try this question again, put alpha equals 1% and run it again, put different percentages for alpha to see how it impacts on the results. But alpha is 5% and the p-value is 6%. Can you see that? The p-value is 6%. If you're not sure that that's 6%, just click on it and go up to it. And then hit percentage on it, and it's going to show you that it's 6%. So you can see from that point that 6% is greater than 5%. So again, it's giving us do not reject. So that's one result. What other results can we have had for this? Let's see. What else could we have checked? Let's check second thing, which is the columns, which is the locations. So how many locations did we have? We had 3 locations. So this time for locations, we're going to be testing U1 equals mu2 equals mu3. So we had those 3 locations in Ohio, and we're going to check to see if the salary between the locations is the same or if it's different. If we reject the hypothesis, it means they're not all the same. So not all the same. Again, we're going to get a test. It's going to be the same test. One tail rejection to the right. Critical value. I'll show the do not reject in green. So do not reject over here. And we're going to get the reject in red. And as for the second test that we're doing on the locations, what do we have? We have the critical value is 3.88. So let's put in the critical value as 3.88. And the test statistic is 4.69. So the 4.69 for the test statistic is going to be out here somewhere. So our conclusion is reject 8-0. So reject 8-0 and go with the alternative. So saying for the different locations, the average salaries are not all the same. So they may be the same between industries, but in locations they're not the same. And is that possible? Yeah, it is, because it could be, let's suppose our two industries are plumbers and electricians. And let's just suppose we've got two locations. We've got Los Angeles and New York. So what this is saying is that when we're comparing industries, plumbers and electricians earn the same amount of money. But when we're comparing locations, they do not earn the same amount of money by location. So it could be, I'll give you an example, that it could be that plumbers and electricians in California earn $200 a day. They both earn the same, $200 a day in California. And it could be that plumbers and electricians in New York earn $250 a day. They both earn $250 a day. So they're earning the same amount when they're working in New York, plumbers and electricians, and plumbers and electricians are earning the same $200 when they're working in California. But there's a difference between the salaries in California and New York. So this is what this is suggesting. Now there's a third test we can do on the interaction. Now the interaction, the test that we do on interaction is to test, the null hypothesis will be to test to see if there's no interaction. So let's put H0. Just means no interaction. They don't interfere with each other. And if they don't interfere with each other, we can use the results from above. If they do interfere with each other, we cannot use the results from above. And we're going to have to run two separate tests, two individual tests, single ANOVA tests, one on location and one on industry. The alternative hypothesis here will be HA, that there is interaction. And we're going to actually conduct the same test we did before for the previous two. So the test is going to be a one-tail test with rejection to the right-hand side. Critical value is going to be here. Do not reject is going to be to the left, same as the tests above. Look, do not reject is over here. Reject is going to be over to the right-hand side over here. And we need to go for the interaction. So for interaction, we're looking at the critical value is 3.9. 3.9. And the 3.9, and the F-test statistic is 1.5. 1.5 is going to be here somewhere. So that's going to be do not reject. We go with the null hypothesis. So that means there's no interaction, so those results are sound. Again, we could have got those results from the p value. It's because alpha, if we take again alpha to be 5%, and the p-value for this one was, it was 25%. So the alpha is 5%. The p-value is 25%. That's a big p-value, 25%. Wow, there you go, right there. So that means that alpha is smaller than the p-value. And when alpha is smaller than the p-value, what did we say? When alpha is smaller than the p-value, we do not reject H0. So again, we get do not reject H0 if you use the p-value to do this test. And as an exercise now, I would go through to replicate the table below. So I would leave the sums of squares values in here, and I would go through to verify for myself the degrees of freedom, divide out, get the p-values, the f-criticals. You use exactly the same technique we used on the previous video. So we've got factor A and factor B. Just to cite off industry, we have 2 industries, so the degrees of freedom are number of industries, if we look at the table over here, -1. And then we have, for the second factor, is locations. Well, we had 3 locations, and this is saying it's 3 locations -1. That's how we get the 2 in there. And for the interaction, it's 2. The interaction, if you look at interaction over here, it's just multiplying out these guys, the previous 2. So 1 times 2 is 2. That's how they come up with this figure over here. And then within the 12, how did they get the 12? It's A times B, so it's going to be 2 times 3. It's going to be 2 industries and 3 locations. 2 times 3 is 6. And the number of times we repeated the experiment -1. So we repeated the experiment 3 times, -1 is 2. So it's going to be 2 times 3 times 2. And that's how they get the 12 in here. And the 17 comes from adding these up. And the total number of times they ran the experiment is got to be 18. Was it 18? Let's check. Yeah, look at that block in there. It's 18. 18 times they ran the experiment. And I know that because it's that value plus 1. It's this value over here. And if I add 1 to it, it gives me the total number of times I ran the experiment. And to get the mean square, it's going to be the sum of the squares divided by the degrees of freedom. So 0.5 divided by 1 is 0.5. And then this number over here, this 0.56, comes from 1.12 divided by 2. And all the way down, just divide these guys out. The f-test statistic, you take the mean square of whatever row you're in, and you always divide it by the error mean square. So that's how you get this value. To get the next test statistic, you take the mean square, and again, you're always dividing by this value in here. I thought that was red. You're always dividing by this value in here. And likewise, when you get down to working out this test statistic, it's going to be this value in here, always divided by this one in here. And then finally, when you're doing your p-values and your f-criticals, it's going to ask you for degrees of freedom. So when you're working on this data here, I think we're too close to the edge for it to work. When you're working on that data, the degrees of freedom that you're going to use to work these 2 out are going to be 1 and 12. When you're working on over here to work out the f-critical and p-value here, the degrees of freedom you're going to use are 2 and 12. So this one is a base one. This error one is a base one. So go through that and verify those to check that you've really understood how to do it.